And we have discussed that the number of offspring per individual is distributed as a binomial distribution, so the mean is 1, but there is some variance around 1. Some individuals happen to produce more than one offspring, like individual 1 here, while some do not produce any offspring at all, like this individual with genotype 5 here. And as a side note, I have mentioned that there are other models other ways to model genetic drift. Perhaps the second most popular model after the Wright-Fisher model is the Moran model, named after Nancy Moran, where the generations can overlap and individuals have some lifespan which is not fixed. So here everyone just survives for one generation. There everyone can just survive for any number of generations, and so the survival is modeled as an exponential process, so that you can survive to some time with exponentially declining probability, and then you can reproduce at some periods of time. And it can be shown that that Moran model can be basically put down to Wright-Fisher model. So all the dynamics that we have talked about yesterday and that we will be talking about today will be very similar, even if we use models that are complicated. So we have discussed how as a result of this randomness in reproduction, the allele frequencies in a population change with time. And again, that has nothing to do with selective differences between the genotypes. Selection is that acts on the genetic component of the differences in number of offspring produced. And here, these differences arise purely due to random reasons, purely due to stochastic, differences in the number of individuals one produces. And as a result of that, and therefore there is no direction of these fluctuations. So they are completely random. They preserve the mean. The mean allele frequency will remain whatever it was in the beginning throughout the life of the population. But in individual runs of such a simulation, one or the other allele will inevitably eventually become fixed. Because once you, in this random fluctuation process, hit the boundary, hit either 1 or 0, there's no way to create new variation unless novel mutations arise. And we were sort of discussing how this analogy, how this is similar to the drunker's walk. And we have derived the equation, which is for some reason not here, but it's just the simple equation for the change in heterozygosity of the population due to genetic drift, which is just proportional to 1 over n. That is, this change happens very rapidly in small populations, and it is almost negligible if n is very large, so that h remains constant for a long time. So this basically means that genetic drift rids the population of variation, like opposite to mutation, which create normal variation. Genetic drift gets rid of this variation. And it can also be shown that the time it takes for an individual mutation to fix is, in this Fisher-Wright model, also similar to the size of the population. And basically it makes sense, so you are sort of walking randomly around like a drunkard, around the value that you started with, so the amount of time it will take you before you actually hit the boundary is similar to the size of the platform divided by the step size. So depending on how many steps it will take you to hit the boundary, that many steps it will take you to hit the boundary eventually, on average. So the average fixation time here is close to n, which is the population size. So one thing that we have sort of swept under the rug so far is that, of course, the real populations are not very similar to the right fisher populations, right? The right fisher population has this ideal structure in which everybody has an equal chance to reproduce, and there is no structure, and all individuals produce the exactly same number of offspring in the expectation. In real life, of course, things can be very different. Yes, and also assume the population size is small. In real life, of course, things can be very different. The population size can change with time. For example, it can fluctuate, increasing in summer and decreasing in winter. Some individuals can just refrain from reproduction, and some individuals perhaps will not be reproducing at all. The population structure may affect who mates with whom, and so forth. So how useful is this right fisher model anyway to think about real life populations? It turns out that it is pretty useful because we can write these very simple dynamics in the right fisher population, but then we can measure the drift in the real life population of our choice that we study, for example, in humans or in mice or in something else, using some metric of drift, and we'll discuss how to measure drift later. And then we will see that the effect, that the strength of the genetic drift is similar to that expected in some ideal right fisher population. And then, even though the size of our population studied will be very different from that of the right fisher population, we can ask, well, what would be the size of the right fisher population that would give us the exact same amount of drift? And that size is something called the effective population size, notated as M sub E. That's effective population size. So the effective population size, once more, is the size of a right fisher population ideal that mates and reproduces according to right fisher laws, that would give you the exact same amount of genetic drift as the size or as the population that you study. So we can talk about the effective population size of humans, for example. That will be the size of this ideal right fisher population, which would have the exact same amount of genetic drift as humans. And the easiest way to measure drift is by the rate of decay of heterozygosity. So if we see that, for example, the variation in this real-life population is changed at this rate, and we know the actual variation, then this immediately gives us the size of the effective population size of the considered population. And so we will talk in a few minutes about how to actually measure the effective population size. But when we do measure it, it almost always turns out that the effective population size is not equal to the real population size. And there are a bunch of reasons for that, of course. So first of all, not all the individuals in a population have to breed. Not all individuals necessarily breed. So if you, there are some males, for example, in many populations that do not simply have the chance to produce offspring because they are not, if we think about mammals, they are not fit enough to conquer a female. If you go to, say, Commandery Islands, which was my experience, to some islands in the far north, there are these huge beaches on which the seals or sea lions lie, and the way it looks is that in the center of this beach there are all the successful males, and each of these males has a harem of its own, consisting of like 10 or 15 females. And then, of course, in the center of the peach, the sex ratio is very much biased towards females, and this single successful male fertilizes mates with all these females. And then on the side of the peach, there are all these males that, wait for their turn, but will probably not get a chance to reproduce ever. So that's something called the bachelor's part of the peach. So that's all the vast majority of males are on the outside of the peach. So they will never get a chance to reproduce most likely. So that would be an example in which the sex ratio is very much biased. So the many of the males will not be reproducing. And it can be shown that in that case, the effective population size is similar to the size of the less reproducing sex, males in this case. So the population size can fluctuate with time. And again, one can show that if it changes with time, then, for example, the numbers of generations in this way. So, for example, we model this right Fisher population, except that it's no longer a right Fisher because we have the changes in sizes of population between generations. Well, it can be shown then that the effective population size is equal to the harmonic mean of all the population sizes in all the generations. Harmonic mean is different from the arithmetic mean in that it is sensitive to the small values. It is most similar to the smallest of the values. So if the population has the size of 10,000 for 9 out of 10 generations, and then of 100 for another 10 generations, then the effective population size will be more similar to 100 than to 10,000. Does that make sense? So that's why the harmonic mean is sensitive to the smallest value, and therefore the population bottlenecks are important.
Can you please close the window?
Can
you please close the window so you can close?
Yes. Okay. So how do we actually find out what how strong the genetic drift is? Well, it turns out it's pretty easy to do that if we account for the mutations. So let us now introduce the model in which we do have drift and we have mutation, and again we'll, as usual, ask if there are any equilibria in this system. So it looks like there can be, right? Mutations create variation, as we have discussed many times, and drift removes variation, gets the population rid of the variation. So let us try and write down the math for this case, and if there is some equilibrium, then we sort of would expect that the change in variability in heterozygosity of the population will be zero, right? Now the change in the heterozygosity is just the result of these changes due to the opposite forces of genetic drift, which removes variation, and mutation, which creates variation. And let's just try writing out what these terms are. So the change in H due to drift, we already know, is minus M divided by H, minus H divided by M. Again, we're talking about the haploid populations here, but it will just be 2M in the case of haploid population. And now we want to ask what is the change in variability due to mutation. And for that, we again have to think of this scheme of reproduction that we've had, right? So we have heterozygosity is the probability that two individuals sampled randomly from these populations, from this later generation population, are different by state. So for this thing to change, we need a mutation to happen at least at one of the lineages leading from the parent to at least one of the offspring, right? So the mutation can happen here, or it can happen here, doesn't matter. It also doesn't matter if we're looking at a single allele here, so the mutations have to happen to change heterozygosity. The mutations have to happen in an individual that has been homozygous, so in between two identical copies of the allele, otherwise they would not make any difference, will not have any effect. But for us, it doesn't matter whether this identity was due to the parent, to these two individuals having a common parent, or to the fact that these parents were different, but the lineages, these two parents were different by identity, but they had the same copy of the alleles that were identical by the state of this allele. So these two situations should be the same. So now, what is the probability that a mutation has happened at least in one of these lineages? Well, it is 1 minus the probability that it hasn't happened in either of these lineages, and so the probability that it has not happened in either of these lineages is the probability that it hasn't. So that's 1 minus the probability that it has not happened in the first lineage, which is 1 minus u. Yes, let's assume that this rate of the mutation is u as usual, or u, whatever. So it has not happened in the first lineage, and it has not happened in the second lineage. These are two independent events, so we have to square that. Okay? So now, yeah, so this is the probability that a mutation will happen at least in one of the lineages, and therefore this whole thing is the probability that it will not happen in either of the lineages. So now, again, let us ignore the small terms u squared, and when we're doing that, we're essentially assuming that the back mutations do not happen. That the mutations that happen only increase their variability, but cannot decrease it. Therefore, all the loss of variability actually happens due to drift, not due to mutation. So then that will be 1 minus 2u, is that right? So that is just, oh sorry, yeah, so this, okay, so I got this wrong. So this is already the probability that the mutation has happened in at least one of the lineages, right? That's what we want for H to happen. But this has to be multiplied by the probability that the ancestor was identical, right? Either here or here. In both cases, the ancestor had to be either the same individual or the genetically identical individuals. And which we discussed yesterday, that is the probability of that is 1 minus h. So that's just homozygosity. Sorry. And so this is the so that's just 1 minus h times 1 minus 2u, right? So that's 1 minus h times 2u. Okay. So again, that's a haploid population. We assume here, if it were diploid, then that would be 2 to n. And so then we are asking whether there is an equilibrium in this change for heterozygosity. So if there is an equilibrium, then the change in h will be equal to the change due to drift plus 2u times 1 minus h, and in equilibrium that will equal 0. So let's solve that. 2u 1 minus h equals h over n. 2nu minus 2nu h equals h. So that's h times 1 plus 2nu equals 2nu. And so the equilibrium value of h then equals to 2nu divided by 1 plus 2nu. This is the answer. So this is the value of heterozygosity in a population that we will have due to joint effect of mutation that creates variation and genetic drift that removes variation. Let's see if it makes sense. If the mutation rate u goes up, becomes very high, then what will h be? If u is infinity. One. So if the mutations, if there's a huge amount of mutation, then the population will be very, very variable. That means no matter which two individuals we pick out of a population randomly, they will be different in this allele that we're looking at. Makes sense? Okay. If u goes to 0, then this thing will be going to what?
0.
To 0. Okay? If there is no mutation, then of course there will be no variability. Drift will get rid of the variability, of the small variability that there is. Now, curiously, the effective population size has the same effect, exact same effect as the mutation rate. And they actually only occur here together in the equation, so you cannot use this equation to distinguish between the two. So if the population becomes very large, that means the drift is inefficient in removing variation. All the variation that comes into the population basically is preserved there. So if NE is infinity, which is sort of the model that we have been thinking about previously, then variability will be accumulated due to these new mutations, and in the absence of drift, and also we're assuming no selection here, these mutations will all be preserved. Conversely, if NE is small, then the mutations will be, the variants that arise due to mutation will be lost due to genetic drift. Hope this makes sense. So now, the funny thing is that, the nice thing about this equation is that H is something that we can measure exactly. H is something that we can measure directly from the current populations. And we have discussed how to do that, right? We can just use the protein sequence alignment from a population and look at what's the probability that two nucleotides in a column in this alignment are different. You have a homework problem on that. So that's not something we call phi there, but this is the same thing that's called H here. And that immediately tells us about the ME times U. And then if we know U, we can also, sometimes we can also measure U. And we have discussed how to measure the mutation rate. There are many ways to do that, right? If we measure U, then we can get an estimate of the effective population size. And then what are the effective population sizes that we actually see if we do that? Surprisingly, it turns out that the range of effective population sizes, the range of MEs, is rather narrow. These very different species, Homo sapiens, fruit fly, nematode worm, ascidian, and a bacteria, they all have rather similar values of the effective population size. Because they all have, well, H, which only differs within a couple of orders of magnitude. And U is, as we know, rather similar throughout the life. However, of course, in reality, the census population sizes, right? The actual number of individuals will be hugely different between the species. How many? Well, we know that the number of, say, nematodes in a cubic centimeter of soil is enormous. So that gives rise to huge estimated population sizes, and there are probably many more bacteria, and the ascidians, the sea covers huge amounts of Earth's surface, so there is enormous amounts of ascidians. So these things differ by many orders of magnitude, while these things differ by just a few orders of magnitude. Also, the effective population sizes tend to be smaller than the census population sizes. Both those findings are sort of curious. We do understand why MEs, we think we understand why MEs are smaller. We have sort of discussed that. Not only individuals produce population sizes with ways and so forth, but why is the range of ME so narrow? And that's actually an open question, I would argue. That's something people do not understand all that well. There are guesses, but none of them are universally accepted. Well, so there was an effort for some time to find the species that would be the most variable, because many people believe that such a species would present a way to address this anemia among others, and so there were, I have mentioned that already, there was this ascidian species, Cylon ascidiani, which was found to have about 8% nucleotide diversity in fourfold degenerate sites. So we want to look at the fourfold degenerate sites here because we're just assuming that genetic drift acts and the mutation acts, but we assume that selection does not act. So that allows us to use, so we want to minimize the pressure of selection in our analysis, and this is where in this model we do not include selection at all, right? So here, these guys saw that in this size the diversity is about 8%, which seemed high. Then Escher-Carter's group found the 14% diversity in the C. Brennery worm, which was even higher. And then Maria Baranova, now Andrianova, who is a TA actually on this course, and a group led, a team led by her, found that in this wood decay mushroom Scatophyllum communa, the diversity is about 20% at synovial size. So there are instances in which species do accumulate large amounts of diversity. And the way asked why is that the case, because the high diversity can arise due both to large values of mutation rate or due to large values of the population size. And it turned out that both these factors play a role. Marshall measures the mutation rate, which turned out to be sort of high per generation in these individuals, and that means that both U is high and N is high. So that was curious. Still, that does not allow us to answer the answer to the question of why this range is so large is still sort of open. Okay, so now I want to talk about the effect of individual, about what happens if in a population a novel mutation arises and then that mutation is subject to genetic drift. So again, there is no selection happening. Let's just try to understand what is the fate of a novel mutation, of a novel allele arising in a population due to mutation. And we can simulate that. So we can start with our simulations, run our simulations with different allele frequencies, and of course the drift will cause these frequencies to fluctuate afterwards. But what we are now specifically interested in is the fate of a new mutation arising in the population. And what we're particularly interested in is how this combination of drift and mutation affects the process of evolution. Because here we have discussed how drift affects the variability within the population. Now, how does it affect the accumulation of replacements, accumulation of substitutions happening in the long run over many generations, substitutions that will be then visible as divergence events between different species. If we compare those species, loss of generations down the line. So we see that here is computer simulations in which novel mutations arise, and we see that the majority of these mutations go extinct, but some of them, even though they are no better, they just happen to be lagging, and they increase in their frequency. Sometimes they still go extinct sometime later, but some very lucky ones increase in their frequency radically and then get fixed in the population, right? So these fixed variants can actually lead to evolution. This is a non-adaptive evolution. There is no selection happening here, but still evolution is proceeding just to mutation and genetic. Let's try to understand what is the rate at which this process happens. And the formal math can be pretty hard, but the intuition behind it and the simplest case is pretty simple. So what we are interested in is the rate k, small k, at which the evolution proceeds due to new mutations arising and then spreading by genetic drift and then getting fixed in the population. So we want to write an equation for k. And this sounds like a complicated task because in general, modeling drift is hard, right? You want to model the distribution of all allele frequencies at each generation down the line, then integrate somehow over time. That sounds complicated, but we can use pretty simple considerations to inform our intuition here. So that's the rate of allele replacements due to novel mutations being fixed by a genetic drift. So for such a replacement to happen, we need two things to happen, right? First, a mutation to occur, and then this mutation to rise in frequency and to get fixed. So the rate at which the novel mutations, remember that we're not looking at population. So we're thinking of a population level process. What is the rate at which a mutation arises? Again, we have some mutation rate U and some population size n. Let's assume I will not be writing this up E here because let's just think about a Fisher-Wright population for a second for simplicity. So n is the population size. So what's the rate at which a novel mutation at this allele arises in a Fisher-Wright population?
NU.
Speak up, someone's here.
NU.
N times U, right? So the mutation can arise in any of the n individuals, and in each individual it will arise with rate U. Is that clear? So that's the process of origin of new mutations. And now the question becomes, well, what's the probability of that such a mutation will get fixed in the course of this process? And does anyone have any idea of how to get that? Well, so the mutation initially, what is the frequency that a mutation here has immediately at the time of its origin? So mutation creates a new variant, which as usual has some allele frequency p, right? What is this p for mutation which has just arose?
1 divided to n.
1 divided by n, right? 1 over n. So there's this new mutation, 1 over n. And we are asking what's the probability that it will go all the way up to fixation. How do we decide that?
1 divided by n, we don't consider cases where mutation could happen at the same time to all individuals. If n is large, n is large.
Right. We're assuming so far that the yes. So that's not a necessary assumption, but for simplicity, let us assume that the mutation rate is rather low, so that there are no mutations, no novel mutations competing with each other in this population. That just simplifies things. So let's assume that the mutations happen either get fixed or get lost before the next mutation in the same site happens. So this sort of contradicts this figure, but let's think that these are many different mutations in many different sites here. And now here we're just considering one site. So we're asking what's the probability that this mutation will get all the way to fixation. And to answer that, you might want to remember what we have discussed yesterday about the genetic drifts removing all the variation. So remember that thought experiment about the people lost on an island and many generations down the line, everyone having the same last name, the same surname, right? So turns out that if we look enough, if we go enough generations into the future, all the individuals here will be descendants of just one single individual here. in this ancestral generation. And that just is the consequence of the random fluctuations in allele frequencies due to genetic drift. So all the lineages will eventually converge or coalesce towards one individual. So just one of these alleles that exist in the population at time t0 will give rise to all the ancestors in the future if we look enough generations into the future. And there's no selection here. Therefore, all these individuals are totally equivalent, right? This individual which has arisen with the frequency, this mutation which has arisen with frequency 1 over n is no different from all the other variants. And therefore, it is exactly similar to all the other guys in its probability to spread to fixation. We know that one of these individuals will give rise to all the individuals in the future. So this one will be that individual with just the probability equal to its frequency. 1 over n. Does that make a little bit of sense? So the probability of fixation of an allele is just equal to its allele frequency. Simply from symmetry considerations, right? Because everyone is similar. If a mutation was at the frequency of 1/2, then the probability that it would be would be fixed would be 50%, and the probability that it would be lost would be 50%. Here, the mutation is at initial frequency 1 over n, so the probability that it will be fixed is again 1 over n, and the probability is that it will be lost is 1 minus 1 over n. Okay? So that's the probability that it will spread. So we have to multiply this by 1 minus n, and we get just 2. So this is an unexpected result, because we are writing the equation for the rate at which the new mutations spread through a population. And that population can be, it has to involve this rate of which new mutations spread through a population. And that population can be of any size. It can even be of a fluctuating size. Still, it turns out that the rate of fixation of novel mutations is just equal to the mutation rate, and we do not have the population size in this equation. That is extremely convenient for lots of different purposes. So this is something called the main equation of the neutral theory. Neutral theory of evolution, and we'll discuss the neutral theory of evolution in a second. So again, this is the figure that explains that if we go enough generations into the future, then all the copies of the allele that we will observe can be traced to a single ancestral individual. A process called coalescence process. That's something we'll discuss later. So the advantageous mutations arise at some frequency and then fix. Okay, so the neutral, let's look at this neutral mutation. So the neutral mutations arising in the population, as we have discussed, spread and are frequently lost, but sometimes the lucky ones are fixed. This happens with a probability of 1 over n per each mutation, and the overall rate of this process turns out to be just equal to the mutation rate. This will not be true for advantageous mutations, because advantageous mutations, the probability of its fixation will be different than 1 over n, because not all the individuals are equal. Some are better in reproducing than others. Okay, so this is, sorry for the acrylic here, this is something we've just derived. The rate of fixation of neutral mutations is equal just to U. And that actually is something that makes the rate of evolution reasonably uniform in time. That is something that establishes the molecular clock. So of course all these, so this is the divergence between the corresponding pairs of species, and this is the fraction of nucleotide substitutions in some gene. I believe this is hemoglobin. This is a pretty old study, which was actually among the first to show that, well, I think the first one to show that the molecular clock is operating, that the rate of evolution is pretty constant in time. And that was pretty surprising because people did know that the population sizes can be very different between these species. So why would that be the case? Well, that would be the case if the mutations are neutral, so that their rate is actually independent of the population size. And then that is actually what allows us to go back to the rate of divergence of species and then estimate the mutation rate from the divergence level. Remember when we discussed the different ways to estimate the mutation level, we had this example in which we were looking at the human and chimpanzee, seeing that they diverged in 1% of their nucleotide positions, sort of guesstimating the number of generations separating these two species, and then dividing the number of mutations by the number of generations and getting something that we call the mutation rate per generation. Well, what we actually got, I don't know if any of you have noticed, but that's not exactly the mutation rate per generation. That's the rate at which new variants get fixed per generation in these huge populations of ancestors of chimpanzees and ancestors of ourselves. So this is exactly what allows us to interpret that value as the mutation rate. And this will only be true if selection is not operating, and conveniently we think that the vast majority of our genome is not under selection. In the past, we can confidently say that in over 80% of our genome, selection is not operating. So therefore, especially if we look at the non-coding, non-functional regions such as intergenic regions and intronic regions away from the genes and away from any regulatory sequences, then these will be a rather robust estimate of the mutation rate that we can get just by looking at the species divergence. Okay, so now we want to ask, what about selective mutations, right? What about mutations that are advantageous? And previously, we sort of assumed that we have modeled selection as a deterministic process. We have discussed how there are two equilibria, 0 and 1, and as long as we deviate from the equilibrium at 0, as long as our new adaptive mutations has some positive allele frequency, no matter how low, it is certain to fix in the population. We have these deterministic dynamics. Is that true if we allow for genetic drift? Because we see that under genetic drift, mutations that are not selected sometimes get fixed. Is it possible that the mutations that are selected nevertheless sometimes do not get fixed? And there the maths, so the answer to that is yes. Sometimes the mutations, even good ones, even giving substantial benefit still do not spread in the population by selection. And here the formal math is a little bit harder, so we'll not be going into it. I will just directly write out the equations, the equation for the rate of fixation of an allele under natural selection. And this equation one can derive in several different ways. Usually it's derived using Kolmogorov backwards equation, so you start from the fact that there is variability and then try to go back in time and derive the dynamics of the changes in allele frequencies based on that. But what I want to do is just to look together with you at this equation and try and understand its basic properties. So this again is the equation written out for the haploids. If we're dealing with diploids, we will just have a 2 here in front of NES. That is the form in which you see it more frequently. And that's the probability that an allele that has some frequency p in the population gets fixed eventually, allowing for the selective preference or selective deficiency of this allele and allowing for genetic drift because we have this effective population size. So one specific case in which we'll be interested is that of a new mutation. So that's the equation for the fixation probability of any variant in the population. But what we are particularly interested in is the probability of fixation of a novel mutation, which, as we've discussed, has this frequency 1/n. And that is 1 minus e times to the NES 1/n divided by 1 minus e times minus e. So now if we again assume that this is a right Fisher population, then NE is the same as N. Now there's this caveat here because here we're talking about actually the rate at which the new mutations arise. And that's what 1/n is about. And NE is about the rate at which these mutations are removed by genetic drift. And therefore, these two things do not necessarily have to be equal. For example, a population can be, if a population is much larger than its effective population size, then these two things will be 1/n can be very small. So n will be very large and NE will be small. So let's ignore that caveat and let's just assume again that we're dealing with the right Fisher population. So then this will be just 1 minus e to the power of minus s divided by 1 minus e to the power of n. So let's first make sure that we replicate the previous results. If selection is absent, so the limit of pi if selection is absent, 1 minus, so this is equals to 1 minus s divided by 1 minus ns. This is just 1/n. So if selection is tends to 0, then the probability of fixation of mutation just goes down to that under genetic. This goes down to 1 over n, as we saw previously. Now let's make some assumptions to see what the dynamics should be under the standard parameters that we're dealing with. And first, let's assume that selection is rather weak, is not too strong. So that's just I just want to simplify the equation a little bit in this extreme. So if selection is much smaller than 1, then 1 minus e to the power of minus s is close to s. And then if so remember that we're talking about meaningful selection coefficients, so the range is about 1%. So that's what will be the case in this scenario. And then let's assume that our population size is substantially large. And ES is much larger than 1. And then then 1 minus e to the power of n es. So if this is very large, this goes to approximately 1. So if this holds, then the probability of fixation of a novel advantageous variant, say a novel advantageous mutation, say with the selection of 1%, with the selective benefit of 1%, is close to x. So this is very far from the scenario, the deterministic scenario that we've discussed previously, where each advantageous mutation was certain to fix. There, each advantageous mutation fixed the probability of 1. Here, if a mutation confers benefit of 1%, it just fixes with the probability of 1%. So 99 out of 100 advantageous mutations that appeared somewhere in a species, each increasing the fitness by 1%, were just lost randomly. Think of all the brilliant adaptations that have happened, but did not happen due to the effect of the random loss of these variants due to genetic drift, just due to the inefficiency of reproduction. Well, due to the randomness of the reproduction. Usually, these 99% are lost at very early stages. So a novel mutation which arises is basically still almost invisible to selection because the drift is operating at very efficiently, very strongly at such low population sizes, and selection is not very efficient. So most of those losses are due to just novel mutations, advantageous mutations arising and then getting lost pretty much immediately. Sometimes an advantageous mutation can raise to some frequency but then become extinct. If an advantageous mutation, say of 1% fitness benefit, rises to the substantial frequency, such as, for example, I don't know, like 10%, then it already becomes defended from drift. It becomes immune to genetic drift, and it's near certain to continue rising in frequency and then get it fixed by selection. In that case, if it happens to rise, if it happens to cross this drift barrier, something people call drift barrier, then it will fix eventually deterministically. Still much depends on luck in these initial early stages of this process. So this is the entire, so here we've made some simplifications, and here is the plot for the equation itself. So this is the probability of a fixation of a novel mutation as a function of 2 NES and 2, because this is that's for diploid population, which will be the same plot just for NES for diploid population. You see that if selection is not, so this is the probability of fixation compared to a neutral mutation. If selection is not operating, then the probability of fixation is exactly that. And then if we increase selection, then the likelihood of fixation becomes higher and higher. And you see that it's similar to NX, and as it goes. So okay, so that's one thing. So selection is inefficient in a sense, in that it does not so drift makes selection inefficient in that it prevents some beneficial mutations from fixation. Another facet of drift is that it sometimes makes the mutations that are deleterious to fix. And we can write out the equation for the rate at which that happens. But so you see that even, say, a rather moderately deleterious mutation with the selective coefficient of -2 NES, so that's mutation that's deleterious, still has some probability of fixation. Still can rise in frequency and spread through population because just drift happens to push it upwards. So that's another inefficiency of the selective process caused by genetic drift. Okay, let's see here. So let's make a, do we want a 5-minute break, or do we just continue straight for another 45 minutes before we switch to the journal clock? Let's continue straight because we had a short session yesterday. So let's discuss then. Now,